Let us start with chapter 2, that is electrostatic potential and capacitance. Let's take a scenario in which if Earth exerts a force on any object, and if you take this object and apply a force opposite to the force that Earth applies on the object. So if you apply it and then with that force applied, you bring the object to a height, let's say h height. Then what happens? At h height, the object gains a kind of energy which is called the potential energy. And this energy is has the formula mgh, where m is the mass, g is the acceleration due to gravity, and h is the height. And that is your potential energy. And the moment you release this force, you just remove the force, then this object will start falling down. And the potential energy, which is due to the height it gains, will be reduced, will becoming less, and the moment it will hit the ground, the potential energy will become zero, because mgh, in that h will become, height will become zero, so whole thing will become zero, so potential energy will become zero. And at this point there will be kinetic energy, and kinetic energy is actually half mv square, and v is the velocity. So the velocity will be maximum when it will be touching the ground. So we have to understand it in a way what book suggests. Then when an external force does work in taking a body from a point to another point, so one point to another point, against a force like the spring force or the gravitational force, so gravitational force was downward and our work done was in opposite direction, the external force was in opposite direction, then the work gets stored as potential energy of the body. So it is get stored as the potential energy of the body. And when the external force is removed, when we removed this force F, we cancelled out, right? The body moves, gaining kinetic energy and losing an equal amount of potential energy. The sum of kinetic energy and potential energy is thus conserved. So always mgh plus half mv square is always conserved. It is the fixed value. So when mgh will become more, half mv will become less, to make it exactly a constant value. And forces of this kind are called conservative forces. So spring force and gravitational forces are example of conservative forces. And Coulomb force is also a conservative force. Why? Because Coulomb force between two stationary charge acts in the same way. All right. Consider an electric field or electrostatic field E due to some charge configuration, which simply means that just think about one charge Q at the origin, and then because of this charge there is electric field, and this charge is positive, so electric field is in outward direction. Okay, so this electric field is there. Now imagine that we bring a test charge Q from a point R to point P against the repulsive force on it due to the charge Q. So let's take one point R here and one point P here, and think about a charge Q, small q, at point P. And if we take this charge small q against the uh, electrostatic field or the force because of charge capital Q, so we just bring it towards the point R and at the point R from point P. And how is this possible? We need to apply an external force. So we need to apply an external force on small charge small q, and this force is the external force, okay, and which is in opposite direction to the force due to the charge capital Q. So this electric field is there, and because of this there is a force on small q, and we have to exert one external force in opposite direction of this existing force due to capital Q, and bring the charge from point P to point R. And what other things we have to keep in mind is that the small charge Q should be very small. Why? Because it should be a test charge, very small in quantity, so that it will not affect the position of the charge capital Q, because small q will also exert a force. Okay, if small q charge is too strong, too big, then it will really exert a force and it will displace our capital Q charge from its position, that is origin, to some other position. Okay, so that's why we will take small q as a test charge, very very small quantity. Second thing, to make it happen, both the charges capital Q and small q should be of the same type, positive positive or negative negative. Then only repulsive force will happen. Then only we can do this experiment that because of capital Q the force is in this direction, and we need to put one external force to bring the charge from point P to point R. Or better I say that in your book the points are opposite. So what I meant P is R and what I meant R is P. So R is the point which is farther from Q, and P is the point which is near from Q. It really doesn't matter, it is just naming the point. So what we are doing is we are taking one test charge from a point R to a point P against the force exerted by capital Q, and to do that the external force works because there is a force, okay, and there is a displacement which is from R to P, okay, this distance is covered. So when this distance is covered, let this distance be a vector R. So when we cover this distance, then it is actually a work done. And since the movement happened in opposite direction of the force, okay, so it is a negative work done. And you apply the same scenario of the conservative forces. The moment you release the external force, the small charge Q will shoot away, again will go back to R. Okay, this is all happening because one external force is applied, and this we are doing to understand what potential is. So potential at point P due to charge capital Q is the work done in bringing a test charge from a point R to point P by applying one external force equal amount of that of the force applied by the charge Q. Since it is very tough to understand what potential energy is, that's why we understand it in terms of the work done. Because work done is a scientific concept already been used and applied earlier. Work done is force multiplied by the displacement. But potential energy is a bit confusing. Why? Because we know about heat energy, light energy, alright, or chemical energy. But potential energy, to understand it in a better way, we need to relate it to the work done. That is why we have all these steps to understand the potential um, at a point and due to a charge. Now, we have discussed already that the work done, which is negative because the external force is in opposite direction of the electrostatic force. So this work done is against electrostatic repulsive force and gets stored as potential energy. So this work done is actually gets stored as potential energy. At every point in electric field, a particle with charge q possesses a certain electrostatic potential energy. To say that wherever you go in wherever you take that charge q, small q, in that electric field, wherever you take it, there will be some potential energy. Okay. So we talked about 2 points. One was P and R. So if you take this charge, just a moment, we talked about 2 points. Okay, the 1 point is P and 1 point is R. And we are taking this charge from R to P. From R to P, point P. And then we say that this at this point a potential is acquired by the charge small q. Okay, this potential is acquired here. But the fact is, even at the point R, there will be some potential because it is still under the influence of electric field. So even at R there is potential. Maybe the value of the potential is different from that at P, but there will be potential. That's why the better way to talk about potential is the potential energy difference. When you take a charged body through the external force from one point to another point, and we call the potential energy difference is equal to potential at P minus potential at R, and that is equal to work done from bringing the charge from point R to P. Displacement is in an opposite sense to the electric force, and hence work done by electric field is negative, and we write minus WRP, work done to bring the charge from R to point P. Alright, and the final definition here for the electric potential difference is electric potential energy difference between 2 points is as the work required to be done by an external force in moving without accelerating, so it is just moving charge q from one point to another for electric field of any arbitrary charge configuration. So we really don't bother about what kind of electric field configuration or charge configuration is set up, the big Q. We don't worry about that right now. Also, the bringing the charge from one point to another, the work done by the external force is exactly equal to the force exerted by the charge Q, capital Q. Why? Because that has to be equal. If there is a difference between these two forces, then there will be acceleration, because there will be excess force, and because of that there will be acceleration, and then we can't say that this is the exact value of the potential. Okay, there will be difference in the potential then. So you have to keep in mind that we have to make sure that the charge which is under motion is not accelerating. And finally, the right side of this equation, what you can see, delta U is equal to UP minus UR is equal to WPRP. Here, the right side depends only on the initial and the final position of the charge. Okay, so to bring the charge from a point R to point P, we only consider the potential at P and the potential at R. Okay, we don't have to consider, or we don't have to worry about in between when the charge is carried from R to P by the external force, where it goes. So if it can go like this also, okay, or like a straight line directly, okay. So potential difference or the potential energy difference is only about the 2 points, the initial point and the final position of the electric charge. Okay, and that's why the force exerted by the charge, the electrostatic force, is a conservative force, because this is one of the fundamental characteristics of the conservative force, that it only depends on the initial and the final positions. The concept of potential energy would not be meaningful if the work depends on the path. The path independence of work done by an electrostatic field can be proved using the Coulomb's law, but we don't need to prove it here. Also keep in mind that actual value of potential energy is not physically significant. It is only the difference of potential energy that is significant. You can see in your book that it is written that we can always add an arbitrary constant alpha to potential energy at every point, since this will not change the potential energy difference. Adding this constant alpha here for the potential energy at P, so potential energy at P is UP plus alpha, and potential energy at R is UR plus alpha. And when we find the potential energy difference, UP minus UR, we simply subtract these two, and then this alpha will be cancelled out. And this builds up to the understanding that if the charge is at infinity, like very far, then there, suppose we can understand that, okay, at that point the potential energy is 0. So electrostatic potential energy is 0 at infinity. And we can say that the work done from bringing the charge, the test charge, from infinity to a point P, that is W infinity P, so from infinity to point P, is potential at P minus potential at infinity. But as we know, potential at infinity is 0, so it will be equal to UP, that potential at P. You might think why all these things are so important, why we have to fix these things like potential at infinity or potential at a point and this constant alpha. But it is just to, develop this concept and develop the topic to define electrostatic potential. But before that, there is a definition that potential energy of charge Q at a point in the presence of electric field due to any charge configuration, that was capital Q, is the work done by the external force. Okay, and this external force is equal and opposite to the electric force. Okay, in bringing the charge Q from infinity to that point. So work done in bringing the charge from infinity to that point. And now we can actually give a name to our potential, or give a sign to our potential, proper sign. And also we'll talk about what kind of force. So force is actually charge multiplied by electric field. So we named the potential at P is Vp, and potential, electrostatic potential. So electrostatic potential at R is Vr. And we can say that this is the work done by external force in bringing a unit positive charge from R to P. And this external force is actually having equal value to, this external force has equal value to QE, but in negative direction, so minus QE. And the final definition of electrostatic potential at that point will be work done by an external force in bringing a unit positive charge from infinity to that point. So potential is actually work done by the charge. And I already told you that this external force is equal to minus Q into electric field. So work done is actually force multiplied by R, the distance. So force, we are taking it as Q into E, electric field, and that has to multiply with R, the distance, and again divided by Q. This is our potential. Okay, and then this will be cancelled out, and we'll find that actually the potential, electrostatic potential V, is something electric field multiplied by R. Okay, the electric field and the one of the distance. And you know that E is equal to 1 upon 4 pi epsilon naught Q upon capital Q upon R square, and that will be multiplied by this R, and the what will happen, will cancel out the square here, and this R will be cancelled out, and our potential will look like something as E is equal to 1 upon 4 pi epsilon naught Q upon R, and it will have a negative sign because our force, external force, is in opposite direction. So this is what you will come finally to, that potential is actually Q by R. So V is proportional to Q by R. Okay, and then we can say that V is equal to minus 1 upon 4 pi epsilon naught Q by R. So far what we have seen, that force is directly proportional to Q1 Q2 divided by R square. Okay, inversely proportional to R square. Electric field is actually Q by R square, and potential is actually just Q by R. We'll focus here on Q by R. We talked about potential as work done by the charge. So the unit of electric potential, that is work done by per unit charge, it simply means work done is measured in joule and charge is measured in coulomb. So joule per coulomb is the unit of this electrostatic potential V. Okay, and this joule per coulomb is given a name, and this name is in the honor of this famous scientist Count Alexandro Volta, and we call this new unit joule per coulomb as volt. And that's why for potential we have used the new sign V. Also, this man is really interesting because he is behind, he is the first person who tried to make a working battery, and because of that today we use our mobile phones, iPads, computers, laptops, the battery is there, and cars and so many things. So this is really an interesting thing to know about the development of battery. Maybe he is the one who started storing that energy in a battery. Alright, after all this talking, I'm sure you are ready to actually explore potential due to a point charge, potential due to other kind of charge configurations, like the electric dipole or a system of charges and continuous charge distribution also. So that we will start in the next video. Thank you.